If we could go out away from the city lights to a dark sky in a remote location on a moonless night and look up, we would see untold number of stars. Each star in the sky is a sun. And if our sun has planets, Mercury, Venus, Earth, Mars, etc., it seems natural to think that other stars should have planets also. And they do. Astronomers have found that each star in our sky has at least one planet. So the next time you're out in a dark sky and look up, you can start wondering about the planets around those other stars, other suns. We have identified thousands of planets around other stars. Hundreds of them are about the size of Earth, and dozens of them are expected to have surface temperatures that are not too hot, not too cold, but just right for life. I'm here to tell you about how I and others are going to be searching for signs of life around these distant planets, far away, orbiting other stars. Now, we're not searching for radio signals concocted by some kind of intelligent little green people far away. We're actually looking for a very, very, very subtle signal, like a whiff of smoke, that could be very hard to detect at all, and also very hard to interpret. I'll start with Earth. Earth is the only planet we know of that has life on it in our solar system and in the entire universe. And we start with a thought experiment. Could we detect life on Earth from afar, given instruments that we commonly use to study planets and other astronomical objects? The answer is yes. And Carl Sagan had a brilliant control experiment. In 1990, when the Galileo spacecraft was on its way to Jupiter, it swung by Earth for a gravity assist. And he had the instruments turned on to look at Earth from far away. And he had his team do like a blind study, pretending they knew nothing about Earth. Could they infer the presence of life on Earth? And what they found were three things that were strongly suggestive of life on Earth. And actually, they chose their wording very carefully, as am I. They didn't say, oh, we've absolutely found it. It was strongly suggestive. Those three things were, number one, abundant gaseous oxygen in the atmosphere. We, as humans, breathe oxygen. Our atmosphere is filled to 20% volume by oxygen. But actually, you know what? Without life on Earth, without plants and photosynthetic bacteria, we would have virtually no oxygen. Number two, they saw a widespread surface pigment that corresponded to no known molecule or mineral. Number three, they observed abundant methane in the atmosphere, which in the presence of oxygen is in extreme thermodynamic disequilibrium. And with these three things, they concluded that there was strong evidence for life on Earth. Here are some images from that experiment. Basically what they're saying is that if you find a bunch of things that don't belong and you work hard to rule out every other possibility, you may actually be left with this suggestion of finding life. And that's what I and others are aiming to do for planets far away around other stars. So let's zoom away from Earth, past the planets in our solar system, past the human-made spacecraft, to a distance of about 1,000 light years. Now, this is actually a real map of real stars, and the highlighted ones are stars with known planets. We know of thousands of exoplanets around other stars. And so the question now is, could we infer the presence of life on Earth if we could have a space telescope and look at a star far away and block out the starlight and see the planet directly? And we are actually trying to build complicated space telescopes. We are building them. We plan to launch them to do so. So the question is, could we see life from very far away? And the answer is yes, for an Earth twin. And in fact, we even know what Earth would look like from that far away. It would look like this. This is a real image of Earth, not from 1,000 light years away, but actually from 4 billion miles away, as taken by the Voyager 1 spacecraft some years ago. Can you see Earth? Believe it or not, that is Earth. It's just amazing. It's a little tiny pale blue dot. This here is light that is scattered in the camera. The red band is light that is scattered in the camera optics, but there's a pale blue dot. I hope some of you are wondering how on earth could we find life just from that little pale blue dot? And in fact, the reason Earth is blue in this image, it's not because of the oceans, which actually are very dark and reflected light. It's because the same reason our sky is blue. It's light scattering off the small particles is blue, and it's actually called Rayleigh scattering. So what we would do is we would need to analyze the light in more detail. And let me explain that by this picture of a rainbow. And here you see this light of the sun is split up into many colors by refraction in a raindrop. Now, if we could look at the rainbow in more detail, in great detail, we'd see some parts of the rainbow are missing. Not whole colors, but just thin lines would be missing. And those are from gases in the sun and in the Earth's atmosphere. And here is a solar spectrum. That's a term for the sun's light split up into colors. And now you can clearly see the parts of the so-called rainbow that are missing. And these are gases that are in the sun's atmosphere that have, I like to say, taken bites out of the spectrum. They prevented some of the light from reaching the detector and the instrument that made this measurement because of the gases just absorbed light. And so here you can see if we could do a class on this and analyze the spectrum and learn all about, you'd have to learn some quantum mechanics and about atoms and other things. We could actually analyze this and find out what is in the sun's photosphere. But we're not going to do that now. Instead, we're going to go to Earth spectrum. And here I'm showing you an image of Earth spectrum. You can see at the bottom a colored rainbow along the bottom. And then you see a squiggly line. We sometimes refer to this as squiggly line science. But what it is you can see, I want you to just see how some of the lines in the solar spectrum, they're very deep. They're very, very dark, perfectly dark. That would correspond to a deep part here. Some of them are more narrow, so there'd be a narrow line like this. Some you can see they're shaded at the edges, and that's why it's sloped here. Now, if the Earth had no gases in the atmosphere, this reflected light spectrum would be a straight line. Okay, and instead it has various gases, and I'm not going to go through what all of them are, but this cartoon does highlight a few of the interesting ones. It has, I'm just now repeating myself, but it has oxygen, is this line here, abundant gaseous oxygen that is made by life on Earth. It has this special, here it's referred to as a vegetation jump, a special pigment. It's not chlorophyll, but it's kind of related. That on plants on Earth have a very strong rise in red in reflectivity. We also have methane, atmospheric methane here, and there are other things also. Water vapor are most of the big features in the Earth spectrum are from water vapor, and that actually is because water vapor is a very strong greenhouse gas. It's highly interactive with radiation, and actually all life on Earth requires liquid water. And so when we look at another Earth, and when we were able to look at spectra of other planets, we'd like to see water vapor in the atmosphere as a sign of surface liquid water. So that's the Earth twin, and this is a real spectrum of Earth, and that's how we're going to hope to find life in the future. But there's one thing here, and that is planets we have found so far, we don't see them in a lot of detail like this image, but we know they're very different from each other. Planets come in all sizes, all masses, all different orbits. And we actually like to say in exoplanets that anything is possible within the laws of physics and chemistry. So given that planets have such huge variety, do you think that the first one we get to see is going to look just like Earth? So that's my job as a professor or a scientist. I think hard about problems, and I'm trying to think through which molecules should it be. How are we going to do this? We're going to build a complicated space telescope and spend a lot of money. We want to know what we're looking for. And it's very hard to think that deeply, that outside of the box. And you know how sometimes when you're working really hard, take a little break, check your email. Well, you know what? Almost every day, like many times a week, when I check my email, I get a crazy theory from someone. I don't know if this happens to anybody here, but someone has usually a theory about some new law of physics or their view of the world. So please don't email me your crazy theory. But I was working on this problem, and I started to realize that, from my view, it seemed like any gas could conceivably be indicative of life if it was produced in high enough quantities. Because life on Earth produces thousands of gases. And and which ones will accumulate and exist in large quantities in an exoplanet, we don't know yet, because the conditions could be very different. Life on those other planets may produce very different things. And here on Earth, much life produces gases for no apparent reason. And so with all that together, I came up with my own crazy theory. And in this theory, I really thought that life produced all small molecules, every small molecule that I could think of. nitrogen, carbon dioxide, hydrogen sulfide, carbon dioxide, oxygen, and those are very small ones, but even bigger ones I could think of. And I thought, wow, I can't believe this. What if this theory is correct? What would it even mean? So I recruited a couple of biochemistry colleagues. We worked on this theory, and then what would I do? I emailed a professor, and he's a Nobel laureate, actually, in the physiology of medicine. And I said, well, can I come and tell you about my theory? And he actually knew me. I wasn't just a random email writer. And he said, okay. So I take my friends, and we go there over across the river to see him. And immediately he said, this is not right. And he pointed out a counterexample of a molecule that's just not produced by life. So we went back to the drawing board, and we worked on it for another year. And we found something something that appears to be very amazing, and that is life seems to produce it produces a large fraction of molecules they're not all standalone molecules. That means they won't exist on their own, but they appear to exist as substructures of other molecules. And what my team found was that some of these that are not produced by life fall into very distinct categories. So life seems to produce many molecules, just not all of them are standalone. And the ones that life doesn't produce, they actually may tell us something very useful about the limits of terrestrial biochemistry. And it may eventually have applications to toxicology or even in pharmaceutical drug discovery. So that was a little aside to just give you a bit of flavor of working as a scientist on exoplanets. But back to exoplanets and atmospheres, I was just going to show you the list of what I started to do. Where I literally wrote a computer code to combine all the important biogenic elements in any combination possible. And we had got this huge, huge list. It ended up being so long, I almost didn't know what to do about it. But thanks for computer programming and computers, and Python language especially, we're able to make a lot of progress on this problem. You can see some molecules, and this is actually only a tiny amount of them, because some molecular formula, there's no molecular structure that matches that formula. Other formula, there are many different incarnations depending on where the atoms are, so you can get lots of them. And in the end, we almost have a list now, I think, of like 20,000 molecules to work with. And that's actually what I'm working on now, is how do we handle the fact that life produces so many different molecules? And on an exoplanet far away, we don't know yet which molecules could be the ones produced by life that accumulate in the atmosphere. But I just want you to know we're working on this, and I have this cartoon to show you that we have thousands of molecules, and we want to sort of filter them out. Which ones are not likely to accumulate? Which ones would not have a spectroscopic line, like the ones I showed you in the solar spectrum? Which ones may also produced by volcanoes? And so we're working through this right now to see what is a possibility and what we should be looking for. So I get the question all the time about why study exoplanets? I mean, we have a lot of problems here. Why are we doing this? Why should we care? And one of my answers is, from a scientist's perspective, is, well, we have this natural curiosity about the world around us. And we'd like to understand, where did our Earth come from? How did our solar system form and evolve? Why is our planet, so far anyway, the only one with life? But a natural scientific curiosity inevitably leads to breakthroughs that were never anticipated, like the laser or GPS. We didn't set out to make GPS so that we could all figure out how to navigate. That came from a big history of people curious about building rockets to us being able to launch spacecraft into low Earth orbit repeatedly. And even the Hubble Space Telescope has many spin-off applications, including medical imaging. One of my favorite reasons for studying exoplanets has to do with space engineering. Exoplanets are so small and so faint and so less massive than their bright adjacent host star that all of the telescopes that we build and ones we're working to be able to find and identify another Earth are very, very complicated. And as a nation, we can't show the world what we can do in space through our defense technologies, which we keep hidden. Instead, through civilian space science, we can showcase our technical prowess. And it's not only that, but the sort of ability to define, think about, and solve very big, complex scientific and technological problems is what we need to be doing to maintain our technological leadership and to train the next generation and inspire them. But for me, my real reason for studying exoplanets is just one of exploration. And here now we're zooming out away from 1,000 light years out to what we think our Milky Way galaxy looks like with hundreds of billions of stars, and highlighted are just the planets, the stars with planets we know about already. And this is our frontier. For me, it's a journey of exploration. We dream big because we can, and we explore because that's part of what it means to be human. Thank you for your attention.